Okay, let's go. So what is the wavelength of the microwave radiation? The frequency is 1.25 times 10 to the 10 hertz. So that's a pretty big frequency. So what do we know about if that's a big frequency? Should the wavelength be small or large? Just based on what we know about how frequency and wavelength are related in respect to electromagnetic radiation. Do we think the wavelength should be a small or a large? Any guesses? Equation C equals lambda times frequency. Nobody? Oh, okay. So we got a couple people saying that the wavelength should be large, and that's a good guess. I can see why you might think that, because this is a large number. You think that the wavelength should be a large number. But when we look at the equation that relates the speed of light to its wavelength and frequency, we realize that if we solve for wavelength, we get C, or wavelength equals C over frequency. And what this now tells us is that frequency is inversely related to the wavelength. So a very large frequency, such as this one, 10 to the power of 10, will give us a very small wavelength. So a very large frequency basically means that the wave, instead of being slow like this, it looks something like this. So we can see that when you have such a high frequency, the wavelength from trough to trough is much smaller versus when the frequency is very very low, or not as large. So we should expect a number that's relatively small. And when we put it into the calculator, we would get 2.998 times 10 to the 8. What is this constant? What is that constant for? Anybody know? This constant represents the speed of light. Exactly, Elias. That's the speed of light, and it's a constant that we should all memorize for the exam, because we're not going to be given that. So we put that into our calculator. So 2.998 times 10 to the 8 divided by 1.258 times 10 to the 10. We get a number of 0.02, and let's just go to 3 signatures. I guess technically it should be 4, so let's go to 4. So 0.2383 meters, which we know is it's not that small. The way you can definitely, like, if you could see the wave, you could see it with the naked eye, just because that's what, like 23. So I don't know, some amount. If you convert it to millimeters, that would be about 23 millimeters, which is, you can see that with the naked eye. So it's not that small, but it's relative to this number, 0.023 is pretty small. Next question is the light with a wavelength of 478 nanometers in blue region of the visible spectrum. Calculate the frequency of the light. So basically, the only important information is this. All this is just there to confuse you. It's asking what is the frequency of the light when given the wavelength, and we know that we should just use this equation: C equals lambda times frequency. And if we're looking for wavelength, it's going to be, if we're looking for frequency, it's going to be frequency is equal to C, speed of light, divided by lambda. So 2.998 times 10 to the 8. Oops. And we divide that by a wavelength of 478 nanometers. So we know 478 nanometers. This needs to be converted to meters for unit reasons because the speed of light is in meters per second. So you need to have the wavelength be in meters as well, not nanometers. We know there's 1 times 10 to the 9 nanometers in 1 meter. This gives us a number that we can plug in of 478 times 10 to the minus 9 meters. So 478 times 10 to the minus 9 meters. And if we put that into our calculator, let's see, 10 to the minus 478, we should get, let's see. So the wavelength is pretty small. Do we expect a large frequency or a small frequency? Large, exactly, Susanna, thank you. Because, like we said earlier, that wavelength and frequency are inversely related, a small wavelength would exhibit a large frequency, is the word I was looking for. So the answer is 6.27 times 10. It's the decimal right here. So 6.27 times 10 to the 14 hertz. That's HZ for hertz. So 6.27 10 to the 14 hertz. This is all stuff we've done already. So let's go ahead and, if there's no questions, let's go on to the next one. What is the energy of a photon corresponding to microwave radiation of frequency 1.258 times 10 to the 10 hertz? So the equation we should be using is what? What would y'all use if this popped up on your exam? Anybody? What about my people on Zoom? E equals H times F, exactly. So as Kennedy said, the equation, there's two equations that relate energy to properties of electromagnetic radiation. The first one is E, no, we do capital E. So E equals H times F, that's the one Kennedy said. And the second one is the energy of the photon is equal to Planck's constant times the speed of light divided by lambda, where lambda is wavelength of the light. Clearly, there's one that we should use because we're given frequency in the problem, we should use the equation that incorporates frequency into the equation. So we could use this one. There would just be a little bit more steps where you would have to use this equation to find lambda using the frequency and the speed of light and plug lambda into this part. So the fastest way is to use this one. So let's go ahead and do that. Planck's constant is 6.626 times 10 to the negative 34 multiplied by the frequency of 1.258 times 10 to the 10. This is equal to our energy. This should give us a nice number of, let's see what it is. 6.626 times 10 to the negative 34. 1.258 times 10 to the 10. 8.33, I got this. 8.335 times 10 to the negative 24, and this would be in units of joules. So again, all these are just plug and chug, and the next one is also plug and chug, but it's not as easy because it's an equation that you probably haven't seen before you got to this class. So does anybody remember the equation? Well, first off, is there any questions on the first three problems? No in the chat if we're all good, and or you can just ask your question. You can unmute or put it in the chat. Yes, perfect. Thank you, Alyssa. Okay, so if there's no questions, let's go on to number 4. Does an electron in a hydrogen atom in the energy level n equals 5 undergoes transition to level or energy level number 3, so n equals 3. What does the Bohr model of the atom predict for the frequency of the emitted radiation? All right, so it's asking for the frequency of the emitted radiation. Is there an equation we should use for this? Maybe not, don't put the equation variables, just type in what the equation is called if you remember it. Anybody? No? It begins with an R. And then the second letter is a Y. And then it goes something like that. Rydberg equation, ring a bell? If not, that's okay. If it doesn't ring a bell, that's all right, because that's why we're doing these problems, is to make sure that these concepts stay, you don't forget about them as you learn new concepts. So that's what we're doing today. Rydberg equation, an electron in a hydrogen atom in the n equals 5 undergoes transition to n equals 3. Okay, so we know that which one is our final n value and which one's our initial. So it starts where and it ends where? Which one's final and which one's initial? Anyone? Or all right, well, it's clear that we're the electron starting in the energy level n equals 5, right? It says it starts there and then it undergoes a transition to energy level 3. So its final destination is the third one. So we can write F here for final. And the initial is the fifth one, right? I'm sure some of y'all were, y'all thought that was the right answer. So initial. Maybe you were just you didn't want to get it wrong, but it's like totally okay if you get something wrong here. It's better to get it wrong now than it is on the test. So feel free to speak up and answer. And the Rydberg equation is 1 over lambda equals negative RH 1 multiplied by 1 over n final squared minus 1 over n initial squared, where our n final is n equals 3 and our initial n is n equals 5. So let's see what we could do here. Lambda equals, I wonder if it's possible to do it a different way, where we know that C equals lambda times frequency. And we know that frequency, because it's asking for frequency, we know frequency, or let's solve for lambda, since that's what we have here. We know lambda is equal to C over F. Because what I was thinking of doing originally, and I don't know if you were thinking, is you solve for this, and then you plug whatever you get for lambda, you plug it straight into this equation here and solve for the frequency. But the math should still work out if we plug this in for lambda. So you would get something that looks like this. Because this holds true, lambda equals speed of light divided by frequency, we can plug C over F in for lambda here. So you should get something that looks like this. And we know that when you have a fraction in the denominator, this denominator F is able to be moved to the top. So it would look something like this. And if you multiply both sides by the speed of light, so multiply both sides by c times c times c, that cancels that. And you should get a final equation that looks like this. And we're going to put the c here in the middle. So in plugging all your numbers in at one time, you can solve for frequency. Or you could have done it the way I said, which would solve for the lambda, the 1 over the lambda, solve for lambda, and then plug that into this equation to solve for frequency. Either one works. I think this is interesting and something new that I've never tried before. So let's see what we get. What's the Rydberg constant for this specific equation? So RH equals 1.097 times 10 to the 7th. Let's see what we got going on. So let's plug all that in. So our frequency is equal to negative. Let's see if I can change this to smaller. 1.097 times 10 to the 7th times 2.998 times 10 to the 8th. And we know that 1 over our final end value was 3. So 1 over 3 squared minus the initial of 1 over where our initial was 5. So 5 squared. And you can simplify this down to 9 and this to 25. Let's see what we get. So negative 2.097 and 7. The 8th, and then 1 over, so 1 over 9 minus 1 divided by . So I think I made a mistake in requiring the negative sign here. I can check with the notes right after this. But if you take the negative sign away, you get 2.338 times 10 to the 14 hertz, which checks out with the answer key. So let me just go check the notes to make sure. I'll go back to it in a second, so give me 1 second. Chapter 7 lecture. Maybe it's in here. Yeah, let me check the lecture. One point zero. Where N1 is greater than 2. If you do it like this, where N1 is the 5, what would I get? -5. Yeah, that's weird. If I do it this way, I still get a negative number, and a negative frequency doesn't make sense. So I want to say that the negative should not be in here when it's final minus initial. Because the key says this is the right answer, not a negative, because you can't have a negative frequency. And so that means that you must not have the negative here if you're doing final minus initial. Okay. Are there any other questions with the, let's see, we're on question 4. I know we kind of went into the question 5 territory. But are there any questions with this part. Again, you could have totally just kept it as the 1 over lambda equals negative or equals RH 1 over n final squared minus 1 over n initial squared.
But if you like math more, you could have done from the way that Dylan just showed. But it's really up to y'all. Doesn't really matter.
So if there's no questions on that, there's the next question requires something called, what, do y'all know what it requires, what equation it requires? What is the wavelength of a neutron traveling at a speed of 4.15 kilometers per second? We know that there is one equation that relates wavelength to speed. Do y'all remember what it is? I think we've gone over it twice already. So hopefully you recall that. If not, again, that's totally okay. Anyone? If you don't know it, say no, so that way I just. But if you do know it, slide that into the chat. And it begins with a D.
And that's what they need.
Okay, maybe not. So it's this equation, de Broglie wavelength equation, which is lambda equals Planck's constant divided by the S mass. So divided by the mass and the velocity. So using this equation, try to solve this problem. So let me rewrite it. So lambda equals h times m times d. So I'll give you 2 minutes to work with this equation. When you're done, chill out and we'll go over it in a second. You want to come do this one?
Yep.
Rich will go over it in about 30 seconds.
Whereas the mass of a neutron is that particular number.
What's particular?
Is it the same as the mass of an electron?
No, remember, massive electron is like super negligible, whereas the nucleus mass of an atom is all of its nucleus, not its electrons.
Wait, the mass of a proton, mass of the electron are not the same?
Proton and electron, no. Why do you think that most of the mass of an atom is in its nucleus, not its? I want to say neutrons and protons are the same, though. I'm pretty sure we can use that.
Okay, sure.
All right, everyone, time is up. So hopefully you had a phone available to you to do a quick videos or not video, web search of what the mass of a neutron is, as it is needed for this problem. And I think for our class, that's something that would be given to you. So this problem should have had the mass of a neutron, and honestly, I did not realize that it was not given to you until Rich pointed that out. So I apologize for that. But do your thing like 21, Rich.
So do you want to go ahead and say the mass of a neutron before we start?
You can go ahead and say.
So it'd be 1.65 times 10 to the negative 27 kilograms. Or something along the lines of that. All right, so what is the wavelength of a neutron traveling at a speed of 4.15 kilometers per second? So we have all the things needed, necessary to solve for a wavelength. We know what Planck's constant is. Can somebody tell me what Planck's constant is? The value for it? Certain number, all of you should memorize. All right, you're on the right track, 6.6. All right, there we go, 6.626 times 10 to the negative 34.
Good job, Elias.
All over your mass of a neutron, which in this case, 1.65 times 10 to the negative 27. And we notice here that we have a speed of 4.15 kilometers per second. Is that the units we want the speed in? Because what is this velocity? What units is that in? Is it in kilometers per second, furlongs per second? What are the units? Meters per second, right? So we need to convert this 4.15 kilometers per second to meters per second. All right, 4.15 kilometers per second. And there is 1 kilometer, there is 1,000 meters. So this would be 4,150. Sorry, not kilometers, meters per second. So 4,150 meters per second. All right, now it's just a matter of plugging everything in to your fancy calculator. 6.626 times 10 to the negative 34. And then this is all over your 1.65 times 10 to the negative 27 times 4,150. And if you plug all that in, you should get a nice answer of 9.6868 times 10 to the negative 11. And what are our units for this answer? So 9.68 times 10 to the negative 11 chickens. That's the units.
Kennedy, what do you think? Grace. Kennedy left me on red. Anyone? Or Gordon? What does that mean?
Forgot. Okay. So 10 to the negative 11. What?
Oh, the unit the variable we're solving for is what? Everyone, we're solving for wave length. Emphasize the length there. So
What's the most common unit for your length?
what is the SI unit for?
Meters.
Exactly.
9.68 times 10 to the negative 11 meters. And that is your answer.
Cool.
All right. Any questions on that? No. Okay. So explain why the following sets of quantum numbers never occur. So all of these are invalid, and we have to try to see why they are invalid. So let's go through all these one by one. N equals 1, sounds good to me. L equals 0, that can happen, right? Can that happen? All right, it can happen. M sub L equals 0. Can that happen?
That's good.
M sub L equals 0 can also happen. All right, what about M sub S equals +1? Can that happen? Why not? What are the only two values my M sub S can be? +1/2, and what else?
Maybe not remember.
-1/2.
You gotta keep your fingers on the tip.
All right, -1/2 +1/2. So since M sub S is +1, so the thing that's wrong with this is M sub S. That's why it's about M sub S. All right, what about for B? N equals 1. Sounds good to me. L equals 3. Is that good? No, why not? Yeah, L, the maximum number L can be is n-1. So in this case, that would just be 0. So since L is 3, there's a problem with that. So L is the problem here. All right, N equals 3, sounds good to me. L equals 2, sounds good to me. What about M sub L? Why not? Yeah, M sub L is larger than or in this case, larger than +2, because the maximum it can go is from -L to +L, which is -2, or sorry, +2, and 3 is greater than 2. So M sub L is the problem here. All right, what about this next one? I have my fingers on it. Okay, M sub L, or what about this? N equals 0. Does that sound good to you? Why not?
That's what.
That's one way to think about it, but yeah, N equals 1, N is any positive integer. So that's from 1 to infinity. So N is the problem here. All right. Now E is the same case as A, N equals 2, sounds good to me. L equals 1, sounds good to me. M sub L is -1, barely, but sounds good to me. M sub S is +3/2. And if you look up here, the only values M sub S can be are -1/2 and +1/2. No 5/2, no 3/2, no 8.5 halves, even though it's not even a thing. M sub S is only -1/2 and +1/2. So the problem here is M sub S. All right, any questions on that? Quantum numbers.
Any questions?
Any at all? None from Elias Atmospheres, okay. Or at the moment, okay. All right, we'll move on. I'm gonna give you all about, let's say, 2 minutes to do this. And for this part of the question, what color is this? Y'all might have to do some Googling. Just stay heads up. So 2 minutes, we'll reconvene at approximately 3:46 to 3:47 p.m.
one of the questions was like, it was like a ketone adding the alpha group to the alpha position of the ketone.
Yeah,
And I was like, okay, so I'm gonna use sodium methoxide because that's what Janice says, but I explained that you use sodium methoxide at room temp for the thermodynamic product. But I would use sodium hydride to completely deprotonate the ketone.
wait, are you talking about the well with cycloheptane?
That's on the. No,
Oh, okay.
that was
Because I was
the,
like, how was kinetic product?
that was one of the roadmap problems.
Oh, okay.
Yeah, so I specifically also wrote like the experimental procedure on how you would do it.
This guy's going extra.
I was like, add the ketone to a solution of sodium hydride in a dropwise manner to prevent the.
Yeah, so one of his regions.
He did, but I knew he probably was looking for the sodium methoxide at room temp.
Yeah.
So I put that.
All right, it is 3:47 PM. So the energy of a photon is 3.34 times 10 to the negative 19 joules. What is the wavelength of the light? So what equation will you use to solve this problem? Something to do with energy, something to do with wavelength.
There's two equations that relate energy to properties of a photon.
But in this case, using one of them might be better than using the other. So what is the equation?
What is
Which
it?
equation?
What do y'all use?
Maybe some like an E. E has to equal something.
Did we all blank out on this? What's the next variable, Rich?
So E equals H.
H times C over
Wave,
H.
yeah, wavelength. I'll take that. E equals HC over lambda.
Perfect.
And specifically, we're trying to solve for the wave. So if we rearrange the equation, lambda equals H times C divided by E. So we can go ahead and plug all our stuff in because we have everything we need in the correct units. So Planck's constant, 6.626 times 10 to the negative 34. Speed of light, 2.998 times 10 to the 8. And this is all over our energy, which is 3.34 times 10 to the negative 19. All right, so if we plug this into our good old fashioned calculator, 626 times 10 to the negative 34 times 2.998 times 10 to the 8th. And that is all divided by 3.34 times the 10 to the negative 19. We will get an answer of 5.95 times 10, 5.95 times 10 to the negative 7 meters. But I'm gonna make an executive decision here. I'm gonna convert this meters into nanometers. Because I know for the color, it's easier to analyze if it's in nanometers. So I'm gonna go ahead and do that. So 1 nanometer has 1 times 10 to the negative 9 meters. So if we go ahead and divide our answer by 1 times 10 to the negative 9, we will get an answer of 594.75 nanometers. And anybody who has Google right now, can you tell me what color that is on the electromagnetic spectrum? I have an idea of what it's around, but I need y'all to confirm with me. Just so we're on the same wavelength. Get it?
This guy. Anyone? I know all of y'all have cell phones, and if you don't, feel bad for you. But everyone should have some sort of device to do a quick search on. Huh. Kennedy, what did you get?
Maybe it's the car I'm using right now. Who knows?
What color is this? You may be asked to do this on the test, so you might as well be familiarize yourself with looking at an electromagnetic. Oh, Elias has an answer.
Light orange. Light orange isn't. I would.
What do you think, Chris?
I mean, me personally. Yeah, I thought it was around like the blue range, like green to blue is what I.
No, I thought. I mean, this is what I guess they're all different, but I'm pretty sure. I'm pretty sure Elias is getting his or her money up.
I'm
I
not.
don't. Yeah, sorry, I don't know.
Oh, okay. I guess, yeah, I didn't use Google for that, so, yeah, Google tells me it is, yeah, light orange to like yellow. Specific, yeah, cause yellow's from 565 to 590.
Ooh,
Oh, wait, 565 to 590, I read this thing completely wrong, okay. So, yeah, light orange is pretty much it. Yeah, so like probably like a orangish color, orange, dark orange, yeah, dark orange, or like something like that.
it's somewhere in that range.
So some orange color, okay?
All right. So it is 3:50. Tomorrow we want to go over electron configurations and identifying paramagnetic atoms versus diamagnetic atoms and ions. So that's what we're going to go over in tomorrow's session. Tomorrow is Friday, and we have a session at 2:30 to 3:30 p.m.
Yeah.
at SEB 3.146. All that information is in the group me. It's pinned up there. So, and again, if you weren't here at the beginning, our Monday session is now being converted to a Gen Chem 2 session because of some interesting circumstances that have transpired this semester. So sorry about that, but please, we'll still have our Thursday and Friday sessions. So with that, y'all are good to go. I mean, y'all been good to go whenever you want. But if there's any questions, we'll stick around for a few more minutes and y'all can ask. So sad John's not here, man.